So we're on the last part of 3A.2, which is just summarizing all the properties of logs. So from logs and natural log, making sure that we're comfortable with being able to identify the major attributes of both types of functions, okay? And again, they're all under the same umbrella. So hopefully it seems fairly easy. This is meant to go fairly quickly. So follow along, ask questions, and just make sure we are all on the same page of what the functions look like, how they move, and how they manipulate. After you finish this, then you're going to have a Desmos practice in your formative assessment to do. No. Yeah. Oh, no, I lied. Exit ticket, Desmos, formative assessment. Got it? It should be viewable now. Don't worry. We're going to get there. Everything's coming together. Life is going to be just fine. All right. So up first is our log parent function. For the log parent function, because your b can be any variable, any value, we're going to just use that b equals 2. And the reason why I typically use b equals 2 is just that it's easier to see those changes in the value because most of us know our multiples of 2, right? 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is, right? Now, for log, it's going to be the opposite of that, right? You're saying 2 to what power makes this? Does that make sense? So when you have your log, you're saying the base to what power makes this. So if I'm using 2, I'm saying 2 to the what power is 1. And you would say, oh, that's 0. That's why I'm at 0. Does that make sense? Then you'd be like, okay, if I'm looking for log 2 of 2, you're asking yourself 2 to what power makes 2, and that would be 1. If I'm looking for log base 2 of 4, you're saying 2 to what power makes 4, which is, good job. If I'm saying log base 2 of 8, I'm saying 2 to what power makes 8, and that would be 3. 2 times 2 times 2 is 2 to what power? Okay? Remember, your log is just the inverse of your exponential. So when you're thinking about it, think about it, asking yourself, this to what power? This to what power? This to what power? And again, it's just easier to kind of see and do that with 2s, all right? Another thing that we're going to pay attention to, so therefore your domain has a starting point. Your domain begins at 0 and continues to positive infinity, which means that your x values have to be greater than 0, not equal to, strictly greater than. Your range has no beginning, no ending. So your range goes from negative infinity to positive infinity, which means that it's all real numbers. You do not have a y-intercept, but you do have an x-intercept, and that x-intercept is going to be at 1, 0. Your domain and your intercept are what they are because you have a vertical asymptote. Okay, we have a vertical asymptote, and that vertical asymptote is at x equals 0. So it's that imaginary boundary line that I'm not crossing. Okay, this is a positive log function, so therefore it is increasing. And when we are increasing, we're going to write it in terms of increasing. So we know that it is increasing, meaning as x goes to positive infinity, f of x is also going to positive infinity. Now, the beauty about log is that this information is the same for all log parent functions, regardless of the base. Okay? So regardless of the base, these properties are going to stay the same. What changes are the values of where these points lie. This point's going to always be here, but this is not, this is not, this is not. It all depends on what your b is. Okay? So as an example, we're going to look at the common log. So attributes of b equals 10. This is called our common log because it's the log. It's going to be the one that's going to be written without. So you would see this written as f of x equals log of x. So when there's no base written, that means that your b equals 10. Does that make sense? So if you look at the calculator or if you turn your phone sideways and you see log, that means that it's a base of 10 is what you're referring to. Okay? Our base of 10 system is what our number system is based off of. So your ones place is 10 to the 0. Your tens place is 10 to the 1. Your hundredths place is 10 to the third. Does that ring a bell a little bit from elementary? Okay. Our common log is what we use most of the time. So as you can see here, it still has the vertical asymptote, that boundary line that it doesn't cross. It still has the x-intercept at 1, 0. And the only one that we can actually graph is log of 10. Because you're asking 10 to what power equals 10? And that would be 1. And outside of that, we wouldn't be able to graph. But everything is the same as far as your property. Your domain is still going to be from 0 to infinity. Your range is from negative infinity to positive infinity. You only have your x-intercept at 1, 0. You still have a vertical asymptote at x equals 0. And the graph is still doing what? Increasing, meaning as x goes to positive infinity, f of x is also going towards positive infinity. And no matter what the base is, these properties are remaining the same. Does that make sense? Okay. And when there's no base present, what does that mean the base is? 10. And that's called our common log. Okay. It is the most common used base of log. Capiche? All right. Here we go. So when we look at our transformation of our parent function, you're still going to have all the transformation rules are going to be the same. So putting it all together, we have that if I have A and you're going to have your F of, I'm sorry, let me write log, not an F. You have A and then you have log. Your B is your base. So we typically we don't worry about horizontal translations, horizontal dilations of logs until later. And we also talk about how they can be manipulated already. And you're going to have your X minus your C plus your D. And everyone has a role. So we're talking about the role starting off with D. Your D is your vertical up and down. So when you have D, if you're adding, you're going up. If you're minusing, you're going down. There's really nothing else to tell you with that, right? Your D is your D. It is what it is, all right? Next up is your C. C is a little trickier, okay? For C, we got to remember that X is a liar. So even though it looks like it's minus C, it's actually going to be shifted to the right. And even though it looks like it's plus C, it's actually being shifted to the left. What also makes C special is that C is your asymptote. This is your vertical asymptote. Okay? If your C changes, your vertical asymptote changes. And remember, it's going to look like a negative C, which is going to make it go to the right. And it's going to look like a plus C, which is going to make it go to the left. Okay? Your A. So your A is your vertical dilation. Which is telling you how much you are stretching or compressing. You are vertically stretching if the absolute value of A is greater than 1, meaning we don't care if it's negative to determine whether it's a stretch or compression. Okay? If the absolute value is greater than 1, then it is a vertical stretch. You're working out more, you're getting skinty. Okay? Vertical compression is a shrink. That means you're working out less and you're getting a little wider. All right. Now, if A is negative, so if A is less than 0, meaning that it is negative, what that's going to do is it's going to affect your domain. Not your domain. It's going to affect your range. Does that make sense? If it's negative, that means you're reflecting over the x-axis. So your range, no, it doesn't change anything. I just lied to you. I don't know why I said that to you. Branch. That's if we were doing horizontal dilations. And we're not doing horizontal dilations yet. We're only doing vertical because we're only in algebra 2. Never mind. It's just a reflection. It's not going to change any properties. Too bad. Darn it. Horizontal dilation fact. Horizontal dilation affects your range. If your domain. You didn't hear me say range. Scratch that. Okay? Y'all are closer to me. All right. So with that being said, you should be able to describe a transformation before having to graph it in a calculator. And am I crazy not to think that you're going to graph it in the calculator if I ask you which graph this is? No, I'm not crazy. I know you're going to graph in the calculator, but you should have the skills to be able to tell me what transformations are taking place. And then you can graph it on your own and graph and do all those things. So what we're going to do is we're going to look at our examples here and we're going to describe what transformation took place. And I'm going to let you graph it on your own to figure out the rest. Does that make sense? All right. So starting here, we have log base. I'm going to call this y1 so I can separate the two when I write it out. We have y1 and y2. So looking at y1, we want to know what is the transformation from our parent function here. So y1, what is this transformation? Transformation. What happened? It's 4 to the left. It's a 4 units left. Good job. Y2, what is its transformation? And Y2 would be 4 units up. Make sense? So you should be able to do that without graphing, knowing the transformation rule. So if you had to choose between multiple choice and you're trying to decide, oh, I wonder which is which, should you be able to say, oh, this one went left, this went right, this went up, this went down. Does that make sense? Okay. The other thing I want to highlight again is that if I am shifting left or right, that not only is just a transformation, but it affects my domain, right? So that means now that your domain for this one no longer starts at 0. It now starts at what kind of floor? Negative, because I went to the left. So now your domain starts at -4 and goes to infinity. So now we're going to take a look at that on the calculator so you can see the transformations. But my main goal is that you could be able to do it without a calculator to tell me what takes place. Every transformation has a starting point. So whether that starting point is a parent function or a given function, in this case, it's a parent function. So I'm going to start there. Alpha window. So my parent function is log base 2 of x. And then after I do log base 2 of x, it wants me to do log base 2 of x. And I have x plus 4. And then my other one's going to be log base 2 of x. And we have x plus 4 on the outside. So when I hit graph, it's going to graph my parent function. So there's my parent function. And then my y2, notice how it translated 4 units to the left. And then my y3 is my up transformation. Do we see how all are adjusted? We all have that visual without me actually having to physically graph it for you in your notes. Easy peasy. If you're using the handheld calculator, you press Alpha window 5. If you're using Desmos, remember you got to type LOG and you're going to hit Shift Dash so that you can put in your subscript. All right. Yes. Okay. So this one, it gave us the equation and it wanted us to describe. Now, on the next one, we're going to be given our parent function and the transformation. And it wants to describe the transformation that took place and write the function. Yeah, so you can graph it later. I graphed it in the calculator. It's your notes. So if you feel like you need the graph to reference back to, then yes. All right. So the parent function is actually the first one. Okay. A big hint for a parent function to know what your base is you're going to look at the value of 1. So if you look at the value of 1 when y equals 1, that's going to let you know for the log what your base is. Does that make sense? So we're going to identify our 1, and this helps us identify our b. So our b is what? 3. So we know that our parent function is log base 3 of x. And we're asking, what did we do from here to here? What was the transformation? What did it do? Made what negative? The outside. You made your outside. Your coefficient became negative. And that's because it reflected over the x-axis. Do we see that x-axis reflection? Because I reflected over the x-axis, that means I had to change my y values. If I'm reflecting over the x-axis, that means my y's have to change. If it's the y's that's changing, that's your A, right? That's your dilation. So we know that our A has to equal at least -1. Were there any other transformations? I didn't go left, didn't go right. All I did was reflect. Does that make sense? And because simply all I did was reflect, then that means that my y2 negative log base 3 of x. Now, if I had gone left to right, that means I would have my C and my D values, right? That C, if my vertical asymptote had moved, that D, if I had gone up or down. How do we feel about working backwards? Okay. And again, how do we identify what our base of our log is? We look for the what value? The x when y equals 1. Okay. Remember, you're looking for when the x when y equals 1, and that's what you know your log is. Capiche? All right, let's keep it rolling. Up next, profits in dollars. So now we're talking about solving. So of course, all these skills have to come into play for a reason. It comes down to, can you solve? All right. So for our problem, our example here, we have P of x equals -k plus 60 times log base 10 of x, where x is the number of subscriptions sold and k is a constant. Find k if the newspaper makes a profit of $35 from 100 subscriptions. Okay. So they're giving us information. So we're going to read through, we're going to highlight our important things, which is our formula. We're going to identify what it means here. It gave us our profit. So it gave us profit of 35. So we know our P of x, and that came from when our x is 100. Does that make sense? So when you put everything together that we know that P of 100 equals 35. Are you with me? Okay. So what that means is that 35 equals this equation. We don't know our k, plus 60 log. Do I have to write the 10? The 10 is optional, right? Because it's common log, so I can write it or not write it, of 100. So I plugged in 100 because that's what it told us. That's when we get 35, right? So our job here is to get this by itself. And this is considered a non-calculator problem because you should be able to do a little bit of math on your own. Trust the process. So the first thing we're going to do here is simplify this. You're asking yourself log of 100. So you're essentially saying, hey, self, 10 to what power equals 100? And your self is going to tell you what? 2. Good job. So that means that log base of 100 is simply just 2. Yes. 100. Well, you don't need to calculate right now. It's a non-calculator. I said trust the process. Yeah. All right. So log of 100 is simply asking you 10 to what power equals 100? And 10 to the second equals 100. So now we took something that was algebra 2, and now it's down to an algebra 1 pre-algebra problem. Can you solve this? Yeah, we can. So we're going to simplify. What is 60 times 2? Negative k plus 120. And what do I need to do to start getting k by itself? Subtract. So you have 35 minus 120. And then I have a negative and a negative, and that makes them both positive. So we know that k equals 85. Because you had a negative and a negative on both sides. And if I multiply it or divide it, it's going to make them into a positive. Oh, All right. So I am going to talk about if you are a person who's like, oh man, that got a little weird for me. Well, at this point, once here, if you, I'm assuming, got concerned about log of 100, could you put that in the calculator? Yeah. If that was like, I have no clue what that is, I would not judge you and I would not be mad at you. You can always put in the calculator. If you're using the handheld, if you choose to use a handheld, you're going to just press log. And that's because it's just log of 10. And I'm going to type in 100. And it's going to tell me what? 2. Okay. If it's log base 10, I'm just going to press the log button. If it's any other log, we press alpha window 5 and we put in whatever base we need. Okay. So that alpha window 5 allows me to put in whatever base I need. And again, I'm putting in 10 to show you that it's still going to just be 2. Got it? All right. So I told you you could do this in your head. Yes. But if it's like something you are like, I don't want to, all right, type it in. But you could. Okay. All right. The last part is just words. You don't have to write anything down. It's all information that's there. But it's going over natural log. And natural log is when we're using E and LN. Okay. The properties are exactly the same as the other logs. It's just how they appear. Do we all know the irrational number pi? Right? Pi goes on forever. E is like pi. It's irrational. It's just a decimal that goes on forever, but not in a pattern. Okay. And so with E, it just means that you have something that's continuously growing or continuously decaying. Every minute, every second, every hour, every whatever, it is continuously happening, which is why we tend to use E when something is continuously in motion. Does that make sense? The inverse of E is natural log. Okay. So this is our natural base. This is our natural log. Natural base, natural log, natural base, natural log. Got her? All right. Properties are the same. Again, with your base is always at your 1, but then the values are where it gets a little different. Okay. As you can see here, your domain, your range, your x-intercept, y-intercept, asymptotes are all the same. Okay. And then the same thing is going to occur for the transformation. Do y'all have this? Max and min? Okay. I was like, do y'all have this? All right. When you're talking about the max and min over a function that is forever increasing or decreasing, they're going to give you a bound to focus on. You're going to have an interval. You're going to have a lower bound and an upper bound. And that's what you're looking for where the max and min exists. If it's an increasing function, meaning positive, so if your A is positive, that means that you are increasing. Okay? If you are an increasing function, it's always going to be f of your upper bound, meaning it's going to always be the higher value. That's going to be your max. And then the f of your lower bound is going to be your min. So when we look here, we have f of x of log e of x, right? Our a, is our a positive or negative? Our a is positive because there's nothing there, right? Cast with a friendly positive one. So what that tells us is that to find our max, we're going to use our upper bound, and our upper bound is 10. To find our min, we're going to use our lower bound, which is e. Does that make sense? So you're going to find f of 10. That's going to give us our upper bound. That's going to be our max. Then we're going to find f of e, and that's going to give us our lower value, which will be our min. Okay. Are we all comfortable putting this into Desmos? And I can model what to do on an 84 instead. Okay, so I'm going to model this in the 84 because at this point I feel like we're all pretty comfortable plugging into Desmos and finding things. Some of it may be a hiccup with the 84. So with the 84, you have a couple options. You can plug in the equation as is, plugging in the values, or because you know you're doing it multiple times, you can go here. I'm going to clear this out. Second plus 712 clears out my calculator. I'm going to go here. I'm going to put in the equation that's the function that's given to me. So I'm going to press alpha window 5. Now, when you see log base e, you also just have the option to use natural log. Log base e is just ln. That is all it is, okay? This right here means ln. Uh-oh, go back. So when you see log e, that's the same thing as putting in ln. So I'm going to go ahead and put an e. To get my e, I'm going to hit second, ln. And because it's going to ask you to put in a power, you just put in 1. Because it's like, why are you doing this? I'm trying to show my students something. Okay? Now, this time I'm going to just press ln. Because that is what log of base e is. Log of base e is just ln. Log of base e is just ln. And when you're evaluating on here, you have a couple options. You can do it from the table or you can do it from the window. If you're doing it from the window, I think I like from the window, especially since it's updated. You're going to press alpha trace, and it's going to ask you what function do you want to use. Okay, so again, from the window, I'm pressing, for my command, alpha, and then I'm pressing trace. And I'm going to say, well, I want to know what is f of 10. And it's going to say, well, here's your f of 10. I'm going to press it again, alpha trace. Well, what is alpha of 10 for y of 2? Oh my gosh, they're the same thing. Log base e and natural log are the same. What? That's crazy. The other beauty here is that you struggle with rounding on the 84, I can go over here where it says float, switch to round to 3 decimal places for me. And when I go back up here to hit these, it'll be like, all right, got you. Come back up. And it does the rounding for me versus your friend Desmond does. Okay? If I need y, and I need to find 10, right? So we have our f of 10 gave us 2303. Now we need to find E. So I'm going to press again, alpha trace. I'm going to plug it into either one because they are the same. When you're putting E in, it's going to ask you for a power. That power is just simply 1. It's just the calculator is programmed to like, hey, this needs to be something on E. And it's going to tell you answer is just 1. Okay. So that's the only time you're going to be finding the max and the min. So again, if A is positive, that means it's increasing. So your upper bound is going to give you your max. Your lower bound is going to give you your minimum value. So my upper bound was 10, and it gave me my max value of 2.303, right? My lower bound was E, and it gave me the value of 1. If I'm finding multiple values on the calculator, I'm going to use alpha trace, and that basically allows me to use function notation. So alpha trace allows us to use function notation. Oh, that got weird. All right, how do you feel? Okay, the last part is just reminding you that the natural log still has transformations, and the transformations are exactly the same as log. The only difference is how it may look. So if you're in natural log, you would have y equals a natural log of x minus c plus d. But everything is the same role, same position, left, right, up, down, dilate. Okay, so we have plenty to do for the remainder of the period. I surely